All right, here we are again. The next slide we're going to do is involving Le Chatelier's principle. And Le Chatelier's principle is really it's a sort of it's sort of an intuitive understanding of what's going on when we reach equilibrium. And what's equilibrium mean? Well, if we have an equation where we have the low a is the coefficient for the chemical, plus we have b of b, and they're going to go, and the double-headed arrows like this means that it is in dynamic equilibrium, and it's the dynamic part that's the most important part. That means the concentrations of these compounds are static, but, and this is all given by the KEQ, this is called the mass action equation. The mass action equation is products over reactants. Products over reactants. That's like a mantra. 20 years from now, 3 o'clock in the morning, I'm going to call you up and I'm going to say, capital K, and you're going to have to say products over reactants, products over reactants. So it's products over reactants. That means it is the species concentration of C. The brackets mean species concentration. That's the concentration that actually exists in solution, not necessarily how much I put in there, because the reaction changes that, times the species concentration of D raised to the coefficient of D, over top of the species concentration of A raised to the coefficient of A, species concentration of B raised to the coefficient of B. That's a constant. That means this product and division has to equal this at all times. I guess technically it could be much below it, but it can never get larger than this. And it should seek to become this. So what a dynamic equilibrium means is that the concentration, when it's at equilibrium, the concentration of B and the concentration of A and the concentration of C and the concentration of D does not change. They are static. But it's a dynamic equilibrium. That means that the forward reaction is going on. It's just that the reverse reaction is also going on. And the rate of the forward reaction is equal to the rate of the reverse reaction, such that there's no change in the concentration, but there is a turnover, a change in the actual molecules that are involved in this. If I had, say, a solid over here, those molecules that actually made up that solid, some of them would be constantly going back into solution. Some of the molecules in solution would constantly be coming out and being deposited there. But their concentrations remain constant overall. All right? So Le Chatelier's principle basically says that if we have an equilibrium and it's disturbed by the addition or subtraction of some of the molecules in there, some of the chemicals that are involved in it, the equilibrium will shift to offset that change. Whatever change happens, it's going to shift in a way that minimizes or offsets that actual change that happens. So like I said, the big thing is to keep in mind this is a dynamic equilibrium. You remember with kinetics, and this is why we did kinetics first, that the rate of the forward reaction was going to be equal to some small k times the concentration of A times the concentration of B raised to some coefficients that we don't know what they are. They're x and y. They come from the rate limiting step, and we don't know what those coefficients are without performing experiments and everything else. In this case, these coefficients do come from the balanced chemical equation, because even though they're involving the rates, we don't have to know how they're involving the rates. We're only interested in how it involves the concentration. And this tells us how many of these molecules it takes to make this many of these, and so on. So that's why it's mass action. They're used there in mass action. This is the rate of it. So you know that as A and B get smaller, the rate's going to get smaller. Doesn't matter whether it's 0th order, 1st order, 2nd order, 3rd order. It doesn't make any difference. Even 0th order, as the concentration of A and B goes down, the rate of that reaction in that direction slows down. As C and D increases, the rate of the reverse direction is going to be equal to some K times the concentration of C raised to some value times the concentration of D raised to some value. So as the reaction goes forward, the concentration of A and B gets smaller, the rate slows down in the forward direction. The concentrations of C and D build up, the rate in the reverse direction speeds up, the rate increases. Again, 0th order, 1st order, doesn't make any difference. The rate's still going to increase as the concentration increases. And what happens? Eventually it reaches a point where they're equal. The forward reaction equals the reverse reaction, and therefore we have static concentration, but a dynamic equilibrium. And that dynamic equilibrium is the important thing. So let's see how that works, because again, for the most part, and we'll talk about the lab in a second, how you answer the questions and things. But for the most part, this is just a mental exercise. You have to be able to see how things are going to happen. So let's say we have this 2SO2 gas, and we add to it oxygen. You know that oxygen is one of the 7 naturally occurring diatomic molecules. Have no fear of ice cold beer. That's the letters of all the molecules. Have, H for hydrogen, no, N for nitrogen, fear, F for fluorine, of oxygen, ice, iodine, C, cold, chlorine, B, beer, bromine. Okay, so have no fear of ice cold beer. 2SO3 gas is formed in there. So what Le Chatelier's principle tells us is, let's say I have this equilibrium, and it is established in equilibrium, and I pump in oxygen. If I increase this reagent, the reaction must shift to offset that increase. So the way it would shift to offset the increase is it would make more products. This would reduce the amount of this, it would reduce the amount of this, it would increase the amount of this. So if we go up here, the product side would increase, the reactant side would decrease, but that's because one of these was increased significantly, and that threw off the balance here. So we have to increase this and decrease these to get it back to where it forms the constant for the equilibrium again. So we can see that it's going to offset. Now, let's say I was somehow able to pull oxygen out. I put oxygen scrubbers in there, and they scrubbed out the oxygen. I added maybe some iron filings, really finely divided iron filings, and they react with oxygen to form rust, and they tie up the oxygen and remove it because there's no iron in this reaction thing. It just says the oxygen. So if there's a side reaction removing oxygen, it's not involved except for the reduction of oxygen. If I reduce oxygen on this side, then what happens? The equilibrium has to shift to offset that thing. This was reduced, so it has to shift in a direction that makes more of this. Makes more of this and reduces this. But it has to make more of this. Now, obviously, it doesn't make back everything, because if it did, then these would be, that would offset it. It wouldn't equal KEQ, but it shifts in the direction to offset the change that happened in there. So let's go through a couple of examples, and we'll get some understanding and make sure we understand kind of what's going on. So example number 1 in the handout. I have CrO4 2-, which is called what? And that's going to produce Cr2O7 2- and water. Now, normally with an equilibrium, water is not part of the reaction because the molarity of water is 55.6 molar. I know you don't think about water having a molarity. You think about molarity being something in water, but water is a chemical, and therefore there's so many moles per liter of water in water, and it's about 55.6. So it's pretty huge, and it doesn't change. But you can think of, in some of the smaller reactions, you can think of water as being part of the system. And for one of the reactions you're going to do here today, water will be part of the system because it's involving cobalt chloride. And cobalt is a substance that when it gets wet, it turns sort of pinkish, and when it's dry, it's very blue. Actually, I think you're dealing with, do you deal with cobalt? Or, no, I think you're dealing with copper. Copper turns kind of greenish when it gets wet, and it's kind of bluish when it's dry. So water will be involved in that. So let's look at this reaction. That's actually called chromate, and that is dichromate. You should have learned that in GChem 1. So what would happen if I added an acid to this system? Well, what's an acid? You should have hopefully learned that. An acid you can think of as something that produces hydroniums. And in this case, I've written it as H+. Technically in water, it's always going to be H3O+. You don't have bare protons in water. But for simplification here, we'll deal with it like that. So basically, if I added an acid, it's going to increase the H+, and therefore it's going to shift the reaction in this direction. And since this is orange, and this is yellow, if I added an acid to this system, I would see the solution turn more orange. And that would be an indication that it shifted towards reactants. And you're going to do some examples in here, some experiments where you're going to look at a color change. And based on the color change, you need to be able to see how the reaction shifted. I'll talk about that in just a second. So you can see if I added an acid, it's going to turn orange. It's going to shift towards the products. Try to say that. Don't say right or left, because I can write this reaction the other way around. Remember, it's going in both directions. So right and left, yes, most people can understand that, but it's better to say products or reactants, because it's always products and reactants depending on how the equation is written. So you have to write down the equation that you're talking about. And I say that'll be important. We'll talk about that in a second. What if I added chromate? Well, which one's the chromate? Do you remember? This one's the chromate. So if I added chromate, what would happen? It would shift towards the products to get rid of the chromate, and therefore, again, the solution would turn orange. It would become more orange. Okay, this one's a little bit tougher, but let's say I had silver nitrate. And silver nitrate, when it goes into water, can come apart to give me silver plus nitrates, like that. Not very much. It's not very soluble. And I shouldn't write that O3 so far away from the N, but that's just kind of because I was looking at something else. All right, so I have sodium nitrate. I put it into a solution. It's going to dissolve to give me, silver, not sodium, silver nitrate. It's going to dissolve to give me silver and nitrate in the solution. Okay, there's one other thing. Remember, there are what kind of reactions? There are exothermic and endothermic. And chemists, not like engineers do it differently. Chemists look at this from the standpoint of the chemicals in the system. So exothermic reaction, exo means what? Exo means out of, like an exorcist, right? When they did the exorcist, they're getting the devil out. So that's what you can always think of. Exothermic, exorcist, we're getting the energy out. And energy in this case is transferred as heat. So the heat comes out of the chemicals into the surroundings and would heat up the solution. The chemicals are actually losing heat. Heat is coming out of them. So if I have an exothermic reaction, then heat must be a reactant or a product. It has to be a product, right? Because the heat's coming out of the system and it comes out of the system. So I would write heat over here. It'd be just like a chemical. It's part of the system. It's just like a chemical. So this is an exothermic reaction. Heat is given off during the reaction, and therefore it's part of the products. If it was an endothermic, endo means into, endoscopic surgery and things like that from medicine, they always have endoscopic surgery. That means into. If it was an endothermic reaction, heat would need to go into the reaction to get it to proceed forward. So heat would be on this side. In this case, this is exothermic, heat's on this side. So when you're doing these experiments in here, you're going to do some where you heat it up and cool it down, and you're going to see how it shifts. Well, based on that shift, you're saying, well, which way did it shift when I added heat? Then you write the heat on the side that it shifted away from, right? Because when you increase something with Le Chatelier's principle, it shifts to get rid of that thing that you increase. So if you heat it up and you see it shift, it must be shifting to get that heat out of there or into the reaction, either way you want to look at it. But the heat would go on the side it shifted away from, not the side it shifted towards, the side it shifted away from. If you cool it down, then it's going to shift towards the side of heat because you're pulling heat out, and it's going to try and offset that by adding more heat back in, and the way to do that is to shift to the side that has the heat. If I cooled the reaction down, it's going to shift to this direction because I'm going to be pulling heat out almost like I'm trying to create a vacuum, and it's shifting over there to offset that vacuum, okay? So this would be an endothermic reaction. So if I heated up this reaction, what would I expect to see? If I heated up the reaction, I would expect to see more solid form and less of this stuff would be in solution. It would shift towards products because I'm adding heat. This is building up and it's pushing it in that direction, okay? What if I added table salt to this? What would happen then? That's a good question. Well, you should remember from your GChem 1 that you memorized the solubility of a lot of things. And one of the things you memorized was, now there's really simple ones, and then there's a couple other ones. And one of them was that chlorides are soluble, except for 3. There's 3 cations. Remember, when we're talking about solubility products, we're talking about things with cations and anions. There's 3 cations that combine with chloride that are not soluble. And what were those 3? It was silver, mercury, and lead. And actually in that order. Silver is the least soluble. Mercury's quasi-soluble. Lead is fairly soluble. Heated up and lead goes into solution. Lead chloride goes into solution. So silver chloride, very insoluble. So if I add this in, you know, because this is what kind of compound? It's a ionic compound, and I think we talked about this before. If not, that's another mantra. Ionic compounds go into aqueous solutions as their ions. Anything that goes into solution is going to go into solution as Na plus Cl minus. If I take table salt, sodium chloride, I put it into a beaker and I stir it up, there is no sodium chloride in that solution. There are sodium cations and there are chloride anions, but there is no molecule of sodium chloride because molecules of sodium chloride don't exist. When we talk about sodium chloride and you say, well, I can see it, there's molecules there. They're not really molecules, they're what we call formula units because they're crystal lattice structures. And in that crystal lattice structure, there's an equal number of sodiums as there are chlorides. So we say it has a formula unit of sodium chloride, but there are no discrete molecules of sodium chloride. That just doesn't exist. There are of water. If I had really, really tiny tweezers, I could grab a little water molecule and wiggle it around like a chair. You know, it's a discrete unit, and I could throw it over in the corner. There's no such thing as that for ionic compounds. There's just a crystal lattice structure that has a certain proportion of the cations to the anions. So it's an ionic compound. Ionic compounds go into aqueous solutions as their ions. So I put this in solution, I'm going to get this and this. Well, now I have in solution both the silver and the chloride. They're going to combine together to form insoluble silver chloride solid. And what does that do? Which way will this reaction shift? It's going to shift to the products because I'm removing chlorides. Notice adding in the sodium and the chlorine doesn't have any effect upon this equation because there's no sodium or chlorine in this equation. But the chlorides react with the silver. That forms an insoluble precipitant that pulls the silver concentration down to offset that loss of silver over here. More of the sodium nitrate's going to dissolve to go over here to produce more heat and nitrate in the solution. Okay, so that's kind of the basics of everything for Le Chatelier's principle. Let's look over the lab and make sure we understand how we do it. You're going to be filling out this data sheet, and when they talk about the color of the solution, it's going to be shades of blue to green. So, between blue and green, you get some turquoise and some other things. Just write down what you think it looks like best and stuff like that, so you can have something to sort of compare it to. It's a pretty simple solution, a pretty simple procedure. You're going to put that copper chloride solution into 5 test tubes, and then you're going to add increasing amounts of the salt solution. So when you're doing that, you're trying to talk about what happened. Make sure you go into the body and find the equations because you want to state everything sort of based on these equations, okay? This is going to be the equation you're going to use. So look at this equation. You can even write it down in your results when you're answering the questions because you want to state stuff based on the equations as they are here. That's what's going to be done. So initially it's going to be, there's going to be some blue in there. Maybe it's going to go more green or something like that. And then you need to look at this equation, and based on that equation, you need to answer the questions from Le Chatelier's principle. That is, there was an increase in X, Y, or Z, whatever the thing is, whether it's a reactant or a product, whichever chemical it is. There was an increase in X chemical. That was an increase of the reactants. Therefore, it shifted towards the products based on that increase of X chemical. There was an increase in X chemical, and therefore the equilibria shifted towards the reactants to offset that, and so I saw it turn more blue. Or it shifted towards the products, and I saw it turn more green. So remember, you're going to do it based on here, and you have to give specifically from Le Chatelier's principle. This increased. That resulted in a shift towards products or reactants, don't use left and right, and therefore I saw this or that happen in it, okay? So make sure you do it that way. You're going to add addition of water into there. And remember, when you're doing those, for test tube 4 and 5, you're going to do the exact same thing. You're going to add exactly the same amount of salt solution to it. So you won't really see a change there, even though on the table I know it says write down the test tube number 4 and 5. These should be exactly the same because you've added the same thing to them. Then you're going to add water to one, and you're going to compare it to the other. It's always easy to see a color change when you've got something to compare it to. So you're going to add water to one and compare it to the other, and then say, I saw a shift towards here because there was an increase in this, and it shifted towards products or reactants, whichever it was. And then you're going to add the same amount of water to number 5, so they're back to being the same thing. Then you're going to take one of those 4 and put it in some hot water, 5, put it in some cold water. And again, now's the time you're going to take your equilibrium expression and you're going to write heat on one side. And then that's going to be telling you whether it's exothermic or endothermic. So when you're answering the questions, do 2 things. One is make sure you look at these equations to be able to answer they've got all the equations you need inside there. They give you extra ones. It's usually the last equation is the important one that you're going to be used to answering the questions. So look at those equations and then make sure you answer things from the basis of Le Chatelier's principle. That is, this increased or this decreased, and therefore the reaction shifted towards products or reactants to offset that reduction or that increase, to minimize or offset. Offset, I guess, is better, not minimize. You want to offset that change, okay? So make sure you answer the questions, answer them from Le Chatelier's principle standpoint. It's really nice to write down the equilibrium that you're using in there because it makes it easier for you to see it and makes it easier when you answer the questions. And it's not a tough lab. It's going to be a pretty simple lab, but just don't blow it off. Don't wait till the last second and then try and do it. Go ahead and do it ahead of time because it does take a little thought when you need to answer those questions. And so it's not a tough lab, and there's no math that I know of. There's no math involved in it at all. But it's an intuition thing, and it's something you should have an intuition because we're going into equilibria. And the better your intuition is about equilibria, the better other things will be. All right? If you got any questions, concerns, problems with the class, whether it's the lab or the lecture or whatever, shoot me an email. We can set up a Zoom. I'll do a Zoom Tuesday at noon. There's no one showed up for the last couple of office hours Tuesday at noon. If there's a better time, I can't do it Mondays or Wednesdays from noon to 3. I have a lecture for quantitative chemistry. But other than that, if there's a better time, let me know when there's a better time for office hours if people need help with things. So far, everybody's been doing really good. So, I'm assuming there isn't really any problems that anyone's having. Not tough stuff. I think things are a little bit easier doing them from home. Some of that's that you have a little bit of pressure off you from doing it inside the lab, and some is we've made things a little bit simpler because of this. But we're still getting the core concepts, so that's good. We want to make sure you get the core concepts of this because they're important concepts that you carry forward. Other than that, stay safe, try and have fun, and I'll see you next week.